All right, good afternoon, everyone. Let's get started. So today we're going to just finish up quickly with the last slide of the previous unit, which is sort of a motivation for the next unit. So this is the last slide of Unit 3. So basically, we've discussed model order selection in this unit, where we are just choosing the complexity of a model. In the case of a polynomial, we're choosing the polynomial degree d. And so, for example, the kind of choices that we are choosing between would be like, do I use one coefficient? Do I use two features? Do I use three features? And so on. But if you think about it, there's actually more flexibility that may be there for us. For example, maybe I want to use the first and the third features, but not the second. So we don't have that flexibility when we look at things this way. So really, perhaps the problem that we want to solve is which subset of features works best for predicting the target. And so this problem is called feature selection, which is different than model order selection. So, for example, how many choices do we have now when we do feature selection? So, did you have a guess? 2 to the power d. What do you think? Does that sound right? Okay, so let's think about it this way. Each of these features, whether we use it or not, is like a binary choice, right? So we can think of can parameterize the subset by a binary vector of length d, because we have d of these, right? So yes, we do have 2 to the power d different choices of features that we can use at this point. So 2 to the power d possible subsets. So that's a very different problem than the one we were working with in this unit, Unit 3, where we had basically d choices, right? Either I use 1, 2, 3, all the way up to d. So instead of have d choices, I have 2 to the d choices. That's a much more difficult problem. So that's the problem that we're going to tackle next. In Spirit, some things are similar. How do we do this? Well, we can use cross-validation in principle. But the main issue is when d is large enough, we can't just try all the subsets. So we have to do some things that are maybe suboptimal, a little bit more clever. So that brings us to Unit 4, which is basically feature selection is sort of the goal. And then in doing feature selection, we'll learn about some other techniques, lasso, maximum likelihood, which will be useful for moving forward to other units. Okay, so in this unit, we are going to have a demo that focuses on PSA testing. So PSA testing is the main way that prostate cancer is diagnosed in men. It's just something that you can easily get from a blood test. And so what this particular data set did is it measured the PSA levels on 97 men prior to having their prostates removed. Then, once the prostates were removed, they could measure various things, and some things they measured just from the blood itself. So they, at the end of the day, had 8 biometrics. And the question is, now, given these 8 biometrics, can you predict the PSA level? So that's the machine learning problem. And further, something that we haven't really thought of in previous demos is, can we use this to do science? Can we, from this sort of analysis, figure out which of these biometrics are most important for diagnosis? Okay, so that's something new. We've just really focused until now on predicting the target. Now we're saying, not only can I predict the target well, but can I tell you which of my features are most important? So that has a lot of applications. Okay, so that's kind of the high level. So the data set is something that you see this in a lot of machine learning classes. I think it originally appeared in this textbook, which is one of the optional textbooks for our course. These are the definitions of the 8 features. It's not really important to us, right? Because we're just thinking of this as a data set. Let's just work with the data set. You can get this data directly from the Stanford website. The professors who wrote that book were from Stanford. And the way we load it is a little bit different than what we saw in previous units. Here we're using a pandas command, read CSV. CSV file means like a comma separated value file. It's just like a text file. And that's how we're going to get the data. So it's not too difficult. You have to tell it a few things like how's the data separated here? It's separated by tabs. Tell it a few things. And basically you can load the data. Okay, so that's going to be our demo for this unit. So let's get back to sort of the ideas. So the approach we're going to use, not surprisingly, at least to start, is our old friend least squares linear regression. So, all right, so let's see. Ask an easy question is Yan here? Okay, so yeah, how do we write, what's the equation now in terms of the x's and the betas for y hat? Okay. Excellent, yeah, so you got it. So, actually, 16. So basically we have the intercept term beta 0, and then we have slope terms multiplying each of our features. So for this particular demo, y is going to be the log PSA level. These x's are our biometric features. And so you might ask, well, why are we using linear regression? So not surprisingly, we learned about it. We know how to do it. It's easy. You can solve a least squares problem, all that stuff. But here, importantly now, the coefficients that we get are easy to interpret. So this is not always the case for machine learning methods. There's a lot of machine learning methods that the way they work is a bit mysterious. They may give you a nice answer at the end of the day, but you don't really know how they got that answer or how to make sense of it. Linear regression, on the other hand, what it provides you are these values, the beta values, and they directly multiply the features. So what that means is that if one of these values is much larger than the others, that is an indication that that feature is much more important than the others for making that prediction, right? That's true as long as the features are scaled so that they're roughly the same size. Because if one of my features is very tiny, then I'm going to need a very gigantic beta just to have any effect, right? So that would kind of ruin the interpretability. So we have to be a little bit careful. We'll talk about this later. We're going to normalize our data starting in this unit so that these guys have about the same size. And then that way, once we've normalized it, then the betas that we learn bring us meaning in terms of which of the coefficients are most important. So which of the features are most important. So that's going to be very valuable in many applications. So how do we do this? Well, we've seen this before. So to do the fitting, we start out by importing from scikit-learn our linear model library, and then we instantiate our linear model linear regression. I'll explain why. We're gonna set the intercept coefficient to 0 for reasons that will become clear. And this is going to give us our linear regression object. Now, we're going to take a shortcut to doing cross-validation. Previously, when I talked about cross-validation, I showed you some code that had 2 nested for loops and a lot of stuff going on. And I mentioned that we're going to later on learn a quicker way. So this is the quicker way. So scikit-learn has already implemented all that nested for loop stuff for you, so you don't have to do it, because it's a very common procedure. And so this is one of the routines they give you for this. It's called cross-val score. And the way it works is you give it the predictor object, which is this linear regression object. You give it your data set. Separately, you give it the feature matrix and the target vector. You tell it what kind of cross-validation you want to do. So if you put in a number here like CV equals 5, it will do 5-fold cross-validation. However, there's sort of a catch. It doesn't automatically shuffle the data itself. So if there's kind of two ways around that. One way is to shuffle the data yourself at the very beginning, do that manually. Another way to do it is to give it a k-fold regression object. So we saw this back in the unit with the 2 nested for loops. We created this k-fold object, and one of the things that object had in it was all the different index subsets that we used in our nested for loop approach. Well, you can also give that object to this command as the k-fold object. So just a small comment. So what I'm giving it here is a little bit of an advanced variation on that. So when we did k-fold cross-validation before, there was one single shuffling that we used to determine all the different folds, and then we just used those k-folds. So if you want even more randomization, you can have scikit-learn do that several times for different random shufflings. So you might still be doing 5-fold cross-validation, but maybe you're doing it 10 times because you have 10 different data shufflings. That will give you more repeatable results, less variability in the results. You can trust them more. So that's what this RKF object is. It's a repeated k-fold object. You can see the details of it in the full demo. Okay. The last thing we need to give this cross-val score is we have to tell it what metric do we want to compute when we do k-fold cross-validation, or what score function in particular. And here we're telling it use negative mean squared error. Okay, so this is the one that essentially we have been using. Sometimes we've called it RSS. Sometimes we divided that RSS by n and we called it normalized RSS. We also realized that that was like the sample version of the test statistical MSE and so on. Essentially, we're using that. But now you might say, well, why is there this negative there? So this is sort of just a convention that within scikit-learn, all their scores are constructed so that the score gets larger when things are better. And with mean squared error, it's the opposite, right? We want the mean squared error to be small. That's what happens when things are good. So to make it conform to their convention, they use negative mean squared error. Now the negative mean squared error, it's a negative number. As it gets larger, as it gets closer to 0, that's better. So that's why there's a negative, just to make sure that this is a valid score according to how they define it, with higher score means better. Okay, so basically you set up this cross-val score thing, you run it, it does all the cross-validation, it computes many different fits of this k different fits of the linear regularizer, or in this case, depending on how many different repeats you have. And at the end of the day, it gives you a vector of scores, one for each fold. And now you take the mean of that, or negative, to counteract this negative here, and you finally get your cross-val version of your mean squared error for this least squares method. And it turns out that this mean squared error is 0.404, and this is just going to be a reference for us. We'll try to do better with other methods in the future. Okay. So in this first approach, we are simply using all the features. However, we know from the last unit that maybe with modeler selection, by using fewer features, I can do better, and in particular by using the right subset of features, I can do better. So this unit is all about figuring out how do you get that best subset of features. Okay. All right, so are there any questions? What I said so far? Yes.
It's like for the feature selection, is it possible that we just do the linear regression and the beta will just decrease to 0, so we kind of automatically take fully select a feature?
I don't think you will find any of the beta coefficients going to 0 with linear regression. It would be a very rare event if that happened. So yeah, in general, they're not going to be 0. We're going to have to find ways to force them to 0, essentially. Okay, great. Any other questions? Okay, so so let's look at feature selection then. The motivation from the last unit, too many features, large error variance, so can we reduce the number? The question is, which ones do we use? So basically, there's the optimal method. And the optimal approach is pretty simple to describe. You construct every possible subset of features. We said that there's 2 to the power d of them. So that could be a lot if d is large. So for each one of those subsets of features, you fit the least squares regression. You fit the corresponding betas, and you use cross-validation to see how well does that work on some test fold that was not used for training. So we learned various approaches to cross-validation. There's the simple split training test. There's the k-fold cross-validation. You can use whichever one you want. But basically, for every subset then, you're going to get a score, and finally you can just compare your cross-validation scores for all your 2 to the power d subsets, and you just choose, let's say, the lowest mean squared error. Okay, so that's the optimal approach. Trouble is, it's really expensive, especially for most practical values of d. In fact, for most practical values of d, you can't even do it because 2 to the power d is just too large. So it's something that is, yeah, you can use it on toy problems, but in practice, you don't really see it used very often. So in practice, you have other methods which are a lot more computationally friendly for larger d. And we'll go through each of these. The first one is called stepwise selection or stepwise regression. And the next one, correlation-based methods. The ones we'll spend most time on are regularization-based methods such as lasso. Okay, so are there any questions before we move on about this exhaustive search? Because that's sort of the first method. That is the optimal. That's the thing you want to do if you can do it. Any questions on that? Okay. All right, so let's talk about another approach. This is a pretty common one, works pretty well. It's called stepwise selection or stepwise regression. And there's 2 variations of this. There's the forward selection method and the backwards elimination. So let's start with the forward method. So it goes like this. At the first step of this method, you use cross-validation to find the single feature yielding the lowest test RSS. So in other words, you try feature 1 alone. Use cross-validation, figure out how well that did. Then you try feature 2 alone. Try feature 3 alone, all the way up to the D features. So now that you have tested each feature individually, you figure out which is the single best feature, and you add that to a list of the features you will use. Now that you have one in your list, you say which of the remaining D-1 features should I combine with that one to find the best 2 features. So you go through the remaining possibilities, you evaluate all of those D-1, and now you found your second feature that you're going to keep. So now you have a list of 2. Now you have D-2 remaining features, and you do this again. Okay, so every time you're testing on the order of D features, first time D, second time D-1, third time D-2, and you do that D times, so you have on the order of D squared computations to do, D squared subsets you're testing. So this is a lot smaller than 2 to the power D for large values of D. Okay, so that's the approach. In some cases, you can be a little bit more clever. What you'll notice is, generally speaking, when you start with one feature, the performance is terrible. You add another feature, it starts to get better. 3 features starts to get better. Eventually, it will start to get worse because now you're overfitting. So rather than keeping going and trying all the remaining subsets, you just, once it starts to get worse, you just stop and say, all right, I'm done. I saw it peak, now it's getting worse, now I'm overfitting. I'm not going to try anymore because it's just going to overfit more. Okay, so that's one way to stop this early. Another way to stop it early is sometimes maybe you have like thousands of features. You're just going to say, just find me the best up to 100. Beyond that, I'm not going to search for them. So you have a max allowed number of features that you preset. So both of those can get you a reasonable number of features. Okay, so that's forward selection. Any questions about how that works? Okay, is that pretty clear? Okay, the other approach is backwards elimination. So you start out by using all D features, then you go through and you remove one at a time. And you figure out which is the single best one to remove. Okay, so then once you figure out that, then you remove it and you never consider it again. Now you have D minus 1 features. Now you go through them one by one, you remove a single one. You figure out which is the single best of those to remove. Once you remove it, you never consider it again. And you keep doing this to narrow down the number of features. Generally speaking, with all D features, it's going to be overfitting. So as you remove features, performance will get better, MSE will go down. At some point, once you've taken out too many, you're going to bias will be the issue, and you'll start to get worse again. So at that point, you know you're underfitting. So you stop. You say, I peaked. I'm not going to go further into the underfitting regime. I'm going to be done. Or you could also say, like, there's a minimum number allowed features I'm going to use. Either one. So that's the other approach. You start with all of them and you remove one by one until you're happy. Yes?
Do they typically give the same amount of features for like the data set?
What do you mean?
Like if you have like 1,000 different like features you could pick from, and then you start with forward selection. Let's say you get to like forward selection finds out 100 features is good, and then you do the same test on the same data with backwards elimination. Will it be 100? Will it be less than that? Will it be more than that?
I would say in general, it's not going to give you exactly the same models. So both of these methods are suboptimal. They work pretty well, but they're definitely not optimal. So they're both going to arrive at some different suboptimal approximations, different subsets, maybe with different numbers of coefficients. So that's what's going to happen usually. You'd probably be lucky if you found that them giving the same subset, or maybe if the data set was really small, if you had just a few features, there's not that many subsets to choose from. In that case, yes, they might find the same one. Yeah. Okay, good question. Are there any other questions? Yeah.
In the backwards elimination, if you take out one feature after first round, if you take out one feature, how do you know the remote feature is not the best one? So you keep.
How do you know it's the worst?
Yeah.
Well, you don't. So, I mean, you tried removing one at a time, and that seemed, if you considered all the D minus 1 subsets, you found the best one. But the reason that these methods are suboptimal is that they only look ahead one step. It's like they're trying to do this multi-step planning where they remove some multitude of features, but they're only looking ahead one step at a time. So that's not an optimal method. If we live our lives one moment at a time and we don't think ahead to, we lead suboptimal lives, right? So that's the same method, same issue here. So they're suboptimal. They're called greedy or myopic methods. So yeah, they're not guaranteed to give you the best answer, but in practice they do work pretty well. So they're pretty popular methods. And they are implemented in scikit-learn very easily, so you can run them with just, like one line. This RFECV means recursive feature elimination with cross-validation. So it kind of does this whole procedure for you pretty easily. Okay, great. So is these methods making sense? Okay, so we'll compare these to other methods in terms of performance in the demo. Okay, so another approach, totally different strategy here. Here the goal is, let's try to maximize correlation with the target. So, if I have a subset of features and certain features are more correlated with the target, the same way we learned about correlation, like the sample cross covariance, I think what we called it. Like the larger that is, you might say, well, that makes for a better feature. So, so it goes like this. You compute the sample cross correlation or cross covariance between each of your features and the target. So first feature target, second feature target, third feature target. And now you get this list of cross correlations, and now you just rank them. You find, okay, this is the most correlated, this is the second most correlated, and so on. And so now the remaining problem is, how many of these? Do I only use the first most correlated? Do I use the first two most correlated? Do you use the first three most correlated? So now you have a model order selection problem. That problem is not a difficult one to tackle. We know how to tackle it. You just use cross-validation. You try using one or two or three, and finally you come up with your subset of features. So basically, here we have, so for each P is going to be the model order. We're finding the P features that are most correlated with the target. So we're computing this S sub Y xj for each feature index j. And we're going to eventually choose the P values of j, giving the largest absolute value cross correlation. So now we do this for each P, so that's the model order. And then second step, use cross-validation to optimize that model order. Okay, so this is also a suboptimal method. Part of the reason you can see that it's suboptimal is maybe I have two features that are almost identical. And maybe those two have the highest correlation with the target. Well, okay, they're both very correlated to the target, but because they're both almost identical, I shouldn't probably be using both of them, right? If they're giving the same information, I should just use one of them and then throw away the other one. So that's the sort of one of the issues that you can find here, is that when you look at one feature at a time without seeing how it relates to other features, that's suboptimal. And so this is a suboptimal method. There are more sophisticated versions of this, where in addition to looking at correlation with the target, you also penalize correlation with other features. But even those methods are suboptimal as well. So in my experience, this does not work very well in practice. It's a method that is out there, but it's not one that I would typically use. Are there any questions about how we're doing it? Did I explain it well enough? So you just find the correlations between each feature and the target, then you rank those correlations, you rank the features, and now the question is, do I use the single most correlated, the two most correlated, the three? That's a model order selection problem. We know how to solve that. So that's the method. All right, any questions on this? Okay, so so there's a variation on this too, where maybe you say, I don't like correlation because correlation is not really the best descriptor of the relationship between two random variables. Maybe I should use something like mutual information or F values or P values. Now, if you don't know what any of these things are, that's absolutely fine. They're just other ways that you can try to measure the relationships between two different random variables. And you can essentially just try all of them. If you want to try this technique, you could start with correlation, try other ones. You can use cross-validation to figure out which of these seems to work best. And they're all implemented with scikit-learn's select k-best method. So again, it's pretty easy to implement, just a couple lines. Okay, so that's the second method, second suboptimal method we're going to talk about. And like I said, it's the one that I don't recommend this. So moving on to the third kind of family of techniques is called regularization. The idea here, totally different from the previous two, is we have a cost function that we're working with. In this case, it's been RSS. That's the thing we're trying to minimize. So the idea here is you add one more function, you add a penalty, something to this called the regularization term, and that penalty is a penalty for using more features. So essentially, the more features you use, the stronger that penalty gets, and the only way to justify using additional features is if the cost, like RSS, is really going down. So, because when you use RSS alone, as we saw, there's no penalty for adding more features. And if you just look at the training data alone, it always says to select more features. So the idea with regularization is let's try to explicitly add that penalty. And we'll get into all the details. There's basically two versions we're going to look at, which is ridge regression and lasso. So I'll explain now with a little bit more detail about what we mean by this regularization approach. Okay, so let's just remember where we were before, just to set it up. So previously, when we use what we learned back in Unit 2, was we said let's choose the beta that is the minimizer of RSS. So that's what the arg means. That's the minimizer, not just the minimum value of RSS. This is the betas that make it minimum. And again, let's see, RSS, maybe I can use this. So is je fais wang here? Yeah, so how do we define RSS in terms of the y's? Okay. Okay, right. So let's put in the beta just to remind ourselves that. Right, sum I from 1 to n. Right. So this is what we have learned to do. So our goal is to modify this to perform feature selection. Like I said, what we're going to do is we're going to penalize the use of each feature. And what I mean by using a feature is setting beta different from 0. Right? Because if I set beta equal to 0, that means I'm going to cancel the presence of that feature in the model, right? It's just 0 times that feature. It's gone. So to use a feature, we're talking about beta being non-zero. So I want to add some penalty function that penalizes non-zero betas. Somehow, maybe like the larger beta is, the more penalty we get, something like that. Okay. So the idea here is that, of course, that's not our only objective. One of our objectives is to minimize RSS. So we're going to balance between minimizing RSS and minimizing this penalty. So this is how we're going to do it. We're going to now say our new beta hat is going to be arg min of beta of RSS, or actually I'm going to call it some new cost function I'm going to call j as a function of beta, where j is equal to the RSS plus a penalty function, which I'm going to write as phi of beta. Okay, so now I have a sum of two terms, the RSS plus my penalty, and this j, this cost, is the one we want to minimize. This penalty, phi, is somehow, we're going to build it to encourage zero-valued solutions to this problem. Okay, so this is the main idea behind regularization. Is it sort of clear? We're doing it at a high level? Okay, so we're going to look at two different ways to construct this regularizer. The first one is called L2 regularization. And in this case, the regularizer phi of beta is going to be alpha times the sum of j going from 1 to d of beta j squared. L1 regularization is alpha times the sum j going from 1 to d of the absolute value of beta j. Okay, so as you can see, in both cases, the minimum value of the penalty is achieved when all the betas are 0. Right? That's the smallest you can make it, is by setting all the betas to 0. Of course, if you do that, your RSS is probably going to be huge, so the j won't be small. So really, we want to somehow balance between these. We want RSS to be small, but the penalty to also be small. Okay. So a few comments, though, is that even though both of them encourage the beta to be 0, they do it in very different ways. So here's a picture of what happens just looking at the jth term alone. So if we're penalizing the absolute value, we have this red line. And if you look closely, for small values of beta j, the red line really does not want those values to be non-zero. It complains for small beta j when the value is non-zero. On the other hand, quadratic penalty here, it doesn't really care very much when beta is small if it's non-zero. It allows it to be non-zero without much fuss. On the other hand, as beta gets larger, the quadratic penalty complains a lot, whereas this absolute value doesn't care as much. Okay, so that's sort of the intuition here. One of them cares about non-zero beta much more for small beta. The other cares about non-zero beta much more for large beta. So this will actually have a profound effect on how these behave as penalty functions. Okay, any questions about anything so far? All right, so then notice that they both have this alpha term. So the alpha is sort of like an overall strength parameter. The larger alpha is how much is this regularization overall being weighted. And we'll see exactly the effect of that in just a moment. The last thing to notice is that these summations are starting from 1 and not 0. In other words, the intercept term, beta 0, is not penalized. We allow that to be whatever it wants to be. That's sort of taking out these just big shifts in the model, and that's fine. Question?
So in the last homework, we kind of had to look at how feature scaling would affect. Would this affect, like, would features need to be scaled down to some sort of normalized window?
Yes, it's exactly what I think I have in the next 1 or 2 slides. So yes, great question. We will have to worry about feature scaling now that we're considering this regularization. Okay, any other questions on just the regularization itself? Okay, so yeah, so now if you remember in the last homework, when you only do this RSS minimization, there was the problem that you solved, I think it was the last problem, that said if you scale the features x, it actually has no effect whatsoever on the final prediction, right? It makes the coefficients beta smaller or bigger, but the actual prediction doesn't change. Well, now we're not just minimizing RSS, we're also using these penalties. And the thing about these penalties is that they treat all the different beta coefficients the same. And so as a result, this is only going to work well if all the beta coefficients are at the same sort of scale. In other words, if I have one feature that's absolutely tiny, so that I need a gigantic beta just to have that feature really have an effect on my prediction, then that beta would be, perhaps overly penalized here relative to some other beta that doesn't need to be scaled so large. So that's the issue. And so to prevent that situation from happening, we're going to normalize the features. And so the basic thing we want to do is something like set the average value or average squared value of every feature to some constant like 1. So here's like the average squared value for feature j, doing the average over all my data samples. So I want to set this to 1, let's say. That would solve this problem. So one thing we learned is that we can write that average as the sample mean squared plus the sample variance. So just sort of another viewpoint on what we're trying to do if we set that to 1. By the way, this upside down A here, this means for all. This is an abbreviation. Okay, so as we're saying, set these average values equal to 1 for all features j. Okay, so that's how we're solving this problem. Now, there's actually something else we can do which is a bit convenient. So if you remember, when we derived the equation for the intercept term beta 0, we derived it both in unit 1 and unit 2. It ended up that it depends directly on the sample mean of y and the features x. And if the sample means are both 0, then the intercept term goes to 0. And so this is sort of just a convenient thing. It's not absolutely necessary to do this, but it's just, as long as we're going to be scaling the features, maybe we'll just scale them to make that intercept coefficient 0, and then we don't even have to solve for it. So that's the typical approach. Here, remove the mean of y and x, then conveniently you get the least squared beta hat of 0, meaning you don't even need to solve for it. So putting this together, the typical procedure is called standardization. So standardization means you do a shift and a scaling so that your target and features have a sample mean of 0 and a sample variance of 1. So it goes like this. You take the value xij from your data set, you remove x bar j from it, so you're shifting it. So now it's going to be the new shifted features are 0 mean. And then you're going to divide by the standard deviation. Once you do that, these new features, scaled and shifted features, are 0 mean and sample variance 1. So shifting and scaling. And then this arrow basically just means replace. So replace your feature data with this shifted and scaled data. So shifting and scaling together, that's what we mean by standardization. It's not just scaling, but shifting and scaling. So we'll do the same thing to the y's. So yi minus y bar over sy. We'll overwrite our yi's with that. Okay, so this solves two problems, solves a normalization problem, but it also, with the shifting, we know that we're going to get 0 valued intercept, so then we don't even have to solve for it. We won't even write it in our equations anymore when we do this. Okay. Any questions on what we're saying to do here? Okay. Not surprisingly, scikit-learn gives you some nice ways of doing this. So here we're going to use the standard scalar method to do this. So with standard scalar, the first step is you instantiate this object, basically set it up. Once it's set up, you have different functions at your disposal. So the function that we'll use most often is the fit and transform function. So by fit, what we mean is compute these statistics from the data. By transform, what we mean is do the shifting and the scaling. So this function does both. It figures out those and it applies them to the data. So here you're giving it the original feature matrix. It's called x0. And then we're going to call the new standardized one xtr, the training x. Okay, so that's doing it. Now, there's a scalar.transform, and if you do scalar.transform, what that will do is it will apply the shifting and the scaling, but it won't learn them. It will assume that those things have been learned from using either the fit function or the fit transform function previously. So the reason why that is important is that once you've designed your predictor using this standardized training data, this predictor really needs to have that standardization to work well. So when you apply it to some new test data, you must standardize the test data as well. But in fact, you must standardize the test data exactly the same way that you standardize the training data. You have to use exactly the same shift and scale. You cannot compute these quantities from the test data and then, because essentially the problem there is there's a mismatch. You've trained with one shift and scale and now you're testing with a different shift and scale. If you do this, you'll find that your performance is just a little bit worse. So, if you're doing this in the final project, and a lot of students do this in the final project, they find that they get, okay performance, but it's just a little bit worse than your classmates. And then you're struggling, how can I do better in the Kaggle competition? Well, it's because you didn't listen on this one day in class. So please, listen today. This will help you in the project. Okay, so you do this estimation of these statistics from the training data, and then you apply those same statistics to the test data standardization. You don't relearn them. Here's another way to make sense of them. If I have a single test sample, is there any way to learn the standard deviation of those features or targets? No, right? I can't. To estimate standard deviation with sample standard deviation, I need at least 2 numbers. I can't do it with 1. Right? So if you actually tried this with a single test sample, you can't even compute these quantities. So it's kind of silly to try. Okay, so those are the main things here. Any questions on these ideas? So there's just one little detail here. So here I'm fitting and transforming I'm standardizing the features. In this line, standardizing the targets. But if you tried to standardize the targets just with Y0 alone, you would run into this error. You'd throw an error and you'd probably be struggling to figure out what is going on. So what's going on is that this function demands that you give it a matrix and not a vector. So this Y0 is a one-dimensional vector quantity. Scikit-learn wants this to be a 2-dimensional matrix quantity. So what we do with this dot reshape -1, this is essentially a shortcut that says, think of this vector as a matrix with 1 column. So you're reshaping it such that the last dimension, the -1 means last in Python, so the last dimension has, the last second dimension equals 1. So that allows this to be treated as a matrix. This doesn't throw an error. And then now you're saying, okay, remove that last ghost dimension. Rather than having this be a 1-column matrix, I want it to be a 1-dimensional sort of list of numbers, just a vector. Okay, so that's just a comment about where this stuff comes from. Okay. Great. So any questions on the standardization? Yes.
So after, if you completed your model and get your beta coefficients, and you're going to use it on the new data that you got, you always have to standardize the data every time you put it into the function.
Yeah. So when you say use it, do you mean use it as a prediction, or you mean take the new data and use that to add to your training data set? Just to make a prediction, yes. You need to standardize the test data. Is exactly what I mean by this. You have to standardize the test data. But when you do this, these numbers have to be computed on the training, not on the test data.
So whenever the model is used, you always have to use the same.
Yes. Yeah. There is something you can do. I think I might assign a homework problem on this where once you compute these betas, you can actually transform them. If you know these numbers, you can transform them into a new beta that will work without any scaling. It's possible to do that, but most people don't do that. They just, once they figure out this way of transforming their data, their training data, they use that same thing to transform their test data. So yeah, the answer is yes. And by the way, there's different ways to do this. This this is standard scaler is using sample mean and sample standard deviation. There's a robust version that tries to be a little bit more tolerant to outliers in your data, points that are really different than the rest, because those points can really throw off sample mean and sample standard deviation. So there's other options, and sometimes on the project, people try those other options, and sometimes they help a little bit. Robust scaler is one. There's various other options you can use, but they all work exactly the same way. The syntax is identical. You can just try different things. Okay. Great. So let's come back to where we were. So we were learning about this idea, and we now have two different penalty functions in mind: L2 regularization, L1 regularization. So it turns out that when you use these, there's particular names for the final results. So when you combine RSS with L2 regularization, for some reason, this is called ridge regression. On the other hand, when you combine RSS with L1 regularization, it's called lasso. Lasso stands for the least absolute selection and shrinkage operator. It's a mouthful, so people just call it lasso. But that's what you get when you combine L2 and RSS. There's another way we can write this. It's a little bit more convenient than writing it with the summations. So how do I write RSS without a summation? Let's see, is Ferdu Wahid here?
No.
Yeah, so how do you remember how we write RSS with a norm? Forgot, that's all right. So we're going to have the norm of the y vector minus the x vector times, or x matrix times a beta vector squared, because this is actually the sum of squares, so that's the squared norm. And then we have another term now, which is alpha times the squared norm of the beta vector. Okay, so that's a more concise way of writing the same thing. Now, someone might notice something that's a little bit different from the way we previously have been writing things. Does anybody notice anything strange about how we're writing this? So previously, we always put an A matrix here, right? But now I'm using an X matrix. So why is that?
Would you remove the beta 0?
Right, exactly. So now beta 0 is 0, so I don't have to add the ones column onto the X matrix. So I'm just using the X matrix alone. And this beta vector, notice that it does not contain the beta 0 anymore, because we know beta 0 is 0, so we're not even considering an inner model. Okay, so let me just... No beta 0 term is in there. Okay, so for the lasso, we have the same RSS term. The second term, we're going to use a notation where we put a 1 subscript here. So this tells us we're using what's called the L1 norm, which, as you can see, is just going to be the sum of the absolute value of the coefficients. That's what this is. This other norm here, sometimes you can write it also with a subscript 2. That's the Euclidean norm, the kind of straight line distance between 2 points that we typically think of, sum of squares. And so this one is a sum of absolute values, which is a different way of measuring distances. And like I mentioned once before, if you're a taxi driver in Manhattan and you want to pick up someone, you would measure distance by how many blocks you have to travel one way and how many blocks you have to travel the other way. That's the notion of distance, sum of absolute values, rather than square root of the sum of squares, like the crow would fly. And so they're just different measures of the length of a vector here and here. Yes?
Why
Why does the L2 regularization have an absolute values around the beta sub j?
It doesn't need to be. I guess, just making it look similar, but squared. But yeah, you could remove the absolute values because we're dealing with real numbers. They're not complex, so has no effect. Okay, so so that's Ridge and Lasso. This is a good time to stop, but what we'll do next time is we'll understand how these work, why they work, how you select the alpha and all that stuff. So we'll save this till next time. So see you guys on Friday then.